Hey everyone, it's Professor Deborah Oakley again here with another example problem. This time we're going to be solving for beam reactions for more complicated loading. And this is really an example of how to apply the principle of moments. And as I will show you here, the problems that involve moment analysis really are all the same problem when they're reduced down to the basic constituents. So let's have a look at this problem and see how this works out. First off, we have a simply supported beam with a cantilever overhang. It's supported on a roller on the left hand, 9 feet from the free end, and on a pin on the right end. 2 kip per foot continuously uniform load across the 9-foot cantilever, 1 kip per foot over the 18 feet, 2/3 of the beam on the simple span portion, and an 8 kip load 9 feet away, 1 kip per foot on the middle part. So the first thing we need to do is to understand how these distributed loads act essentially as concentrated loads. Anytime you think about a rectangle that has a center of gravity, it's always going to act through the middle of that structure, through the middle of that object. So this is essentially what's happening. If this is our total weight, the balance point is through the center. So all of these distributed loads behave in the same manner. The equivalent total load acts through the center of gravity of each of these portions. So we have a portion over here, and a portion over here. And so we take the entire load times the distance that it is operating on. So we can see right here 1 kip per foot over 18 feet is going to be 18 kips. Let's call this W1 and W2. Make that a little bit more clear. So W1 is 2 kips per foot. What I want to do is turn this into the equivalent total load. So that is given by our capital W as opposed to lowercase w for a distributed load. That's 2 kips per foot multiplied by the distance it's acting, 9 feet. And you see that feet will cancel, and we have 18 kips. That's the total equivalent load acting through the center here. And I will call this P1 equivalent is 18 kips. So as not to confuse that with an actual load of 18 kips at this point. Similarly, we have W2 is 1 kip per foot. Now I'm just going to write this out on this line here. It's acting over a distance of 18 feet. And again, our feet cancel, and we come up with another 18 kips for this load, acting through the middle of this structure, or this portion of the structure. Once we've done that, then we're done with looking at the distributed load. Now it's important to understand the reason I call this equivalent is that the behavior of the beam will be very different when it's loaded as a distributed load versus a concentrated load. So let's redraw this now as the equivalent beam, just to make things really, really clear. Now the roller support can only support a force perpendicular to its surface, so I'm going to place that with an arrow, and I'll put a vertical arrow in for the right-hand reaction. Now I have no horizontally acting loads here, so one of our linear equations, sum of the forces horizontally equals 0. There's nothing to do here. It just equals 0. There is no horizontal action. That means there's no horizontal reaction. This has the potential for taking a reaction, but there's no force, therefore no action. So let's put our 18 kips, our true load, then our equivalent 18 kips, Then our other equivalent 18 kips. And that's what it looks like. So it effectively behaves for the reactions in the same as 3 concentrated loads, keeping in mind that this is not a concentrated load in reality. Now, most engineering textbooks you'll find, in fact almost every book you will find, this step is not done separately. It's just simply combined into the moment equation to calculate the total force. But we're separating it here for clarity. And let's get some distances here. This is acting through the center, so this is 4.5 feet. It acts through the center here. Now this is not drawn to any particular scale. It might be a little bit off. In fact, it looks like it is. This is 9 feet, half of 18 feet. And then another 9 feet, and another 9 feet. So I'm going to set this up and redraw this yet again, because I need to use my rotational equilibrium equation. And I want to look at this starting off on the right-hand side here. Look at all the loads that have a tendency to rotate relative to this point here. So it's against the 18 kips here. And just for simplicity, I'll just draw that as an arrow. This is 18 kips. This is 18 kips. And then our reaction here, this is our unknown, this is our left. That's what we're trying to find. And all of these 4 forces, 3 applied loads, 1 reaction, will have a tendency to rotate relative to the right-hand side. So our left, that's at a distance of 27 feet, 18 plus 9. The load of 18 kips, that's a little bit further. That's 27 plus 4.5. That's 31.5 feet. Then I have 18 kips here, that's at 9 feet, and another 18 kips, that's at 9 feet plus 9 feet, 18 kips. So we'll call this point R for the right-hand reaction, and I'm going to sum moments about point R. I'm going to call clockwise positive. So that means that every force that has a tendency to rotate in a clockwise direction will be called positive, and anything in the counterclockwise direction will be negative. So this 18 kips here would, if tethered to this point, would want to rotate counterclockwise. In fact, that's true of all of these, so they're all negative 18 kips. I'm sorry, this is not 18. I wrote that wrong. That's 8 kips. So let's start from the left and work over to the right-hand side. I'll leave the reaction for the last term of the equation. 18 kips, this is 31.5 feet from the point R. And it's negative because relative to this, it goes counterclockwise. Then another 18 kips, this time at 18 feet. Then my 8 kip, the only true concentrated force, at 9 feet. And then the only one that has a tendency to rotate clockwise is our left, because it would be a reaction up if all the loads are coming down. And its distance is 27 feet from the right-hand end. So that's our rotational equilibrium equation. It says that all of these forces that have a propensity to rotate around point R will be balanced to 0 because it's not moving. That's a fundamental consideration of equilibrium. So let's multiply all this out. We have our left then, see if I can put this where it won't reflect. Right about there. Let's try that. So I've got 18 times 31.5. 567. 18 times 18. I'm going to add that to the 567. It's 891. Plus 8 times 9, 72. Add that to the others, it's 963. We'll divide that by 27 feet. Feet will cancel, so we're left with kips. This is a force calculation, therefore units need to be in force. So let's divide that by 27 now, and we get 35.67 as our reaction. Now that one is fairly straightforward because all of the forces acting are going in one direction and reacting go in the other direction. From here, we could calculate the other reaction by vertical equilibrium. Sum of the forces vertical equal to 0 because there's only one unknown, the r right. However, if we do that, if we've made an error here, then we can't be certain that our answer is going to be correct. So if we do the moment equation on the opposite side, then we're guaranteed. That's one of the things that is unique about moment calculations in equilibrium. It always balances to 0. So let's look at that on the opposite side. Put that right there. So what I want to do is actually drop these lines down. I've got a different grid pattern on here, so it won't line up quite the same, but we'll get it close. So again, I've got 18 kips here. Here, 8 kips here, and a reaction on the right-hand side. This is my unknown now. I'm going to sum moments about this point, about my left-hand reaction. In so doing, I eliminate this from the equation because the moment arm is 0. I could sum moments anywhere along here, but I'd have to include this. Now if I include this, it's no better than if I do a vertical equilibrium equation, because if this is wrong, then my other answer is going to be wrong. If I sum moments here, I have one unknown, therefore I solve for that, then my check will be vertical equilibrium. So let's get our distances again. This is 4.5 feet. This will be 9 feet. This is going to be 18 feet, and then our right is 27 feet. So my moment sum now is about the left-hand end. So two things I always want to do. One is to make sure I indicate my moment center. A moment only means something relative to a particular point, so make sure you indicate where that moment center is. Also, I want to remind myself which direction I'm calling positive. Different textbooks will do this differently. There's no absolute positive or negative. There's only really counterclockwise and clockwise. So I'm calling positive clockwise here. That means that these two forces, the 18 kips and the 8 kips, both rotate in a positive direction, whereas this is the difference from the last one. 18 kips here rotates counterclockwise, so it's actually subtracting from these guys. And then the reaction on the right-hand side also has to go counterclockwise, the same as the 18 kips. So you can see how reduction of the complex problem to its essential parts makes it a lot easier to see this rotational equilibrium. So then let's write out all the terms. I've got 18 kips at 4.5 feet. Relative to this position, it goes counterclockwise, therefore it's negative. Then I have 18 kips at 9 feet. That's positive because it would go clockwise. Similarly, I have 8 kips at 18 feet. And then the R right, since it has to go up to balance the downward loads, would tend to go counterclockwise. So it's minus R right, and that's 27 feet away. And all of that together has to be balanced equal to 0. So again, we'll multiply this out. So I've got 18 so that's negative 81 plus 162. Oops, this is kip feet. Make sure you keep your units straight. This is a moment calculation, must be force times distance. So I'm going to subtract 81 from 162. Okay, whoops. Gives me 81. And then 8 at 18, 144. Add that. And once again, our feet are going to cancel. Equals 8.33 kips. Now, here's the last step. Let's make sure that we're correct by doing a vertical equilibrium equation. So now I say sum of the forces vertically are equal to 0. Well, that's really simple. I've got negative 18 kips minus 18 kips minus 8 kips plus the reaction on the left-hand side, upward reaction, plus the reaction on the right-hand side, another upward reaction, all equals 0. So this, add these all up, I got 44 kips equals R left plus R right. So let's put in R left and R right previously calculated. We have 35.67 kips and 8.33 kips. And I get 44 kips equals 44 kips, and it checks OK. So any of these problems that you do, you can make up your own problems. Just verify that it equals 0 and you're pretty darn sure that you're correct. So this is how you take a complicated problem such as this cantilever overhang and simplify it to basic constituents. The key step here making sure that you understand that a distributed load can be treated as an equivalent concentrated load. It's not the same when we get to the beams. That's going to be very different when we size beams. But for the reaction calculations, we can do this. And again, most textbooks, what you would see here instead of 18 kips, this would be 2 kips per foot times 18 feet, then times 4.5 feet. And you just have to understand that this here is the equivalent P. So I've separated out that step just for clarity, and I recommend that beginning students do that as well. So I hope that's helpful and moves you one step closer in your understanding of this material. That's all for now. Bye-bye.